You know, there's a force that holds you in your chair right now. It pins the oceans to the surface of our world, and it holds our world in a delicate, life-giving dance around a star. It's a force so utterly familiar, so woven into the fabric of our everyday experience, that we almost never give it a second thought. It's gravity. And the most astonishing thing about it, the central truth from which everything else flows, is that every single piece of matter in the universe exerts a gentle, attractive pull on every other piece of matter. Not some pieces, not just the big ones, every single one. There's a whisper of a gravitational force between you and the person passing you in the street, between the coins in your pocket and the distant moon. You don't perceive it, of course. You can't feel it. And that's because gravity is, and I can't stress this enough, phenomenally, almost comically, weak. It probably doesn't seem that way, does it? I mean, it takes a real effort to jump more than a meter into the air before you're pulled unceremoniously back down to Earth. But just try this. Hold your arm out horizontally, just hold it there. The entire gravitational force of our planet, countless quadrillions of tons of rock and iron, is pulling on your arm. And yet, the simple electrochemical force in your muscles is enough to defy it. The entire Earth cannot pull your arm down. That's how feeble gravity truly is. Despite this fundamental weakness, gravity has a unique property. It's cumulative, unlike nature's other great forces like electromagnetism, which comes in attractive and repulsive forms that tend to cancel each other out in any normal bit of matter. Gravity only ever pulls. It's always attractive, and so its effect builds and builds. The more matter you gather together, the stronger its gravitational pull becomes. This is why gravity is utterly negligible on the scale of people walking down the street, but it becomes the undisputed master of the cosmos on the scale of planets, stars, and entire galaxies. In fact, you can work out the point where it takes over. Think of an atom. At its heart is a positively charged nucleus, and orbiting it are negatively charged electrons. It's the electrical repulsion between the electrons of one atom and the next that keeps matter solid, that stops you from falling through the floor. In the simplest atom, hydrogen, the gravitational force between its proton and its electron is about 10,000 billion times weaker than the electrical force. It's a number so vast it almost loses meaning. But if you gather enough atoms together, more than about 10 to the power of 40 of them, the cumulative, ever-attractive pull of gravity finally wins out over the cancelling forces of electricity. For a body made of rock, that number of atoms corresponds to a diameter of about 600 kilometers. For something made of ice, which is easier to compress, it's about 400 kilometers. And once gravity becomes the dominant force, it pulls all that matter into the most compact, efficient shape possible, which is, of course, a sphere. So, the theory predicts that any rocky body in our solar system bigger than 600 kilometers across ought to be a sphere, and anything smaller should be an irregular, lumpy, potato-like shape. And when we send our probes out into the solar system, that is precisely what we find. It's a beautiful testament to this simple principle. The first inkling of how this force worked actually came not from gravity, but from magnetism. Back in 1600, the English scientist William Gilbert was experimenting with naturally magnetized chunks of magnetite, or lodestones. He found that the more massive a lodestone was, the greater the pull it exerted on a piece of iron. And crucially, he showed the attraction was mutual. The iron pulled on the lodestone just as strongly as the lodestone pulled on the iron. Gilbert had a flash of inspiration. Perhaps this invisible, long-range force was what held the solar system together. His idea captivated Robert Hooke, Isaac Newton's great rival. Hooke, though, realized it couldn't be magnetism. The sun is clearly incandescently hot, and he knew that heating a magnet destroys its power. But the model, the idea of a force reaching out across empty space from one mass to grab another, a force that gets stronger with more mass, a force that is mutual, that stayed with him. He sensed that magnetism was an analogue for the real cosmic puppet master. The detailed clues, however, lay hidden in the painstaking work of Johannes Kepler. Between 1609 and 1619, the German mathematician dedicated himself to analysing the exquisitely precise observations of the planets made by the Danish astronomer Tycho Brahe. After a truly gargantuan effort, he distilled the chaotic dance of the planets into 3 elegant laws. Kepler's second law is particularly profound. It recognises that a planet moves faster when it's closer to the Sun and slower when it's farther away. More precisely, it states that an imaginary line connecting a planet to the Sun sweeps out equal areas in equal amounts of time. Newton realised what this meant. This quantity, what we'd now call orbital angular momentum, could only be constant if the force acting on the planet was directed only towards the Sun. There could be no force pushing it along its path. Just think about how extraordinary that is for a moment. Before Newton, almost everyone who thought about it imagined something actively pushing the planets along. Angels maybe, flying alongside and blowing them, or gently prodding them with their wings. But Newton perceived the hidden message in Kepler's law. There is no force driving the planets around their orbits. They are in motion simply because of inertia, the tendency of a body in motion to stay in motion, a principle he encapsulated in his first law. The planets are constantly trying to fly off in a straight line into the void, but the Sun's gravity is forever pulling them back, bending their straight-line path into a closed, eternal orbit. Now, Newton had to figure out the precise character of this force. How did its strength change with distance? His masterstroke was to guess that gravity is universal. The force that holds the moon in orbit around the Earth is the very same force that pulls an apple from a tree. This was a radical, courageous idea. It flew in the face of centuries of church doctrine that the heavens were perfect, ethereal, and governed by different laws from our grubby terrestrial world. But it allowed Newton to do something incredible, to directly compare the strength of Earth's gravity on a falling apple with its strength on the distant moon. He knew their distances from the centre of the Earth, so he could work out how the force diminished. At first, you might think that's impossible. The apple is falling, but the moon clearly isn't. But this is where Newton's genius shines brightest. He realised that appearances are deceptive. The moon is falling. He imagined a cannon on a high mountain firing a cannonball horizontally. Gravity pulls it down, and it lands some distance away. Fire it faster, and it lands further away. Now he imagined a super cannon, firing the ball at an incredible 18,000 kilometers an hour. At that speed, as fast as the cannonball falls towards the Earth's curved surface falls away beneath it. It never hits the ground. It is, in fact, falling forever in a circle around the Earth. The moon is doing precisely that. It is falling towards the Earth just as surely as an apple falls from a tree. The answer to the question, why don't satellites and the moon fall down, is that they are falling down. They just keep missing the ground. By comparing the acceleration of the apple with the acceleration of the moon, Newton deduced that gravity weakens according to an inverse square law. Double the distance between two bodies, and the gravitational force between them becomes 4 times weaker. Triple the distance, and it becomes 9 times weaker, and so on. It's a beautifully simple, elegant relationship, and with it, Newton was able to show that a planet moving under such a force would orbit the Sun not in a perfect circle, as the Greeks had believed, but in an ellipse. Kepler's first law explained. This was the culmination of decades of work, spurred on by a visit from Edmund Halley, which led Newton to write one of the towering achievements of human thought, the Principia. But Newton's law did more than just explain the orbits of planets. It explained the tides. The rhythmic rise and fall of the oceans are caused principally by the moon and the sun. And it's not gravity itself that creates them, but the difference in gravity across the Earth. The moon's gravity is slightly stronger on the side of the Earth facing it than on the far side. This difference stretches the Earth and its oceans, creating 2 bulges, one facing the moon and one on the opposite side. As the Earth spins on its axis, we rotate through these 2 bulges each day, experiencing 2 high tides. It's not quite every 24 hours, though. It's closer to 25, because as the Earth spins, the moon is also orbiting in the same direction, so our planet has to turn a little bit extra each day to catch up. But what does this gentle cosmic tug-of-war, this subtle stretching of our world, have to do with the very ground beneath our feet and the possibility of life itself. We often think of our planet as solid, but that's not entirely true. The same tidal forces that raise the oceans also act on the solid rock of the Earth. These rock tides cause the ground itself to bulge up and down by about 30 centimeters twice a day. You don't notice it, of course, because everything around you is rising and falling with you. But physicists at CERN, the particle physics laboratory near Geneva, certainly noticed it back in 1992. They found that the energy of the particles in their huge underground accelerator was fluctuating twice every 25 hours. For a while, they were utterly mystified. Then someone realized that the rock in which their 27-kilometer tunnel was buried was being stretched and squeezed by the moon's gravity, changing the circumference of their accelerator by about 1 millimeter and affecting the particles within. But perhaps the most dramatic example of rock tides in our solar system is on Jupiter's moon, Io. The relentless tidal stretching from the giant planet Jupiter and its other moons has heated Io's interior to the point of liquefaction, making it the most volcanically active body we know of. Pound for pound, it generates more internal heat than the Sun. Newton's law of gravity has immense predictive power, but it isn't the final word. As Einstein realized in 1915, the true source of gravity isn't mass, but energy. Mass is a very concentrated form of energy, but other forms have gravity too. Close to the Sun, where gravity is strongest in our solar system, the energy stored in the gravitational field itself begins to have a gravitational effect. This makes gravity slightly stronger than Newton predicted, and it perfectly explains a tiny anomaly in the orbit of the innermost planet, Mercury, which traces out a beautiful, slowly shifting rosette pattern over centuries. But even Einstein's magnificent theory, general relativity, breaks down. At the heart of a black hole and at the very beginning of the universe in the Big Bang, his equations predict a point of infinite density, a singularity, which is nature's way of telling us our theory is incomplete. We need a deeper theory, a quantum theory of gravity. The leading candidate, string theory, suggests that the fundamental constituents of reality aren't point-like particles, but tiny vibrating strings of energy in a 10-dimensional space-time. In this picture, our universe might be a 3-dimensional island, a brain, floating in a higher dimensional space. And this could solve one of the deepest puzzles about gravity. Why is it so mind-bogglingly weak? Perhaps the other forces are pinned to our 3-brain, but gravity alone can leak out into the extra dimensions, diluting its strength and explaining its feebleness. It's a wild idea, but it reminds us that this most familiar of forces, the one that anchors us to our world, may yet hold the deepest secrets of the cosmos. And yet, for all its cosmic grandeur, for all its power to shape galaxies and orchestrate the dance of worlds, gravity is utterly feeble compared to the force that powers our civilization. We have built our modern world by exploiting a force that is 10,000 billion times stronger than gravity. That force is electricity. Just to get a sense of its incredible strength, imagine a mosquito. It's made of atoms just like you and me. At the heart of each atom is a positively charged nucleus, surrounded by a cloud of negatively charged electrons. It's the attraction between these opposite charges that holds the atom together. Now, imagine you could magically remove all the electrons from the mosquito, leaving only the positively charged nuclei behind. Like charges repel, so these nuclei would fly apart with unimaginable violence. The mosquito would explode, not with the force of a firecracker or even a hydrogen bomb, but with the energy of the asteroid impact that wiped out the dinosaurs. That's the power locked away inside every speck of matter, the power of the electric force. We don't notice this phenomenal force in our daily lives because in any normal piece of matter, the amount of positive and negative charge is exquisitely balanced. The forces of attraction and repulsion cancel each other out so perfectly that there's not even the slightest hint that this titan is lurking within. When you walk past someone in the street, you feel no pull, no push, nothing. But if you can create a charge imbalance, as with our imaginary mosquito, you unleash its power. And that is the secret of how electricity runs our world. It's the charge imbalance in a thunderstorm that creates lightning. It's the charge imbalance created in a power station that drives the flow of charge, the electric current, that lights our homes and powers our lives. The story of how we tamed this force is one of serendipity and profound insight. For centuries, electricity and magnetism were seen as separate, curious phenomena. Then, in 1820, the Danish physicist Hans Christian Ørsted, during a lecture to his students, noticed that a wire carrying an electric current deflected a nearby compass needle. An electric current could act like a magnet. This discovery inspired the great English scientist Michael Faraday. Faraday was different. While others focused on the currents flowing through wires, he had this incredible intuition that the empty space around the wires and magnets was where the real action was. He imagined invisible fields of force extending out from charges and magnets. An electric current, he realized, was just a secondary effect, a flow of charges driven by an electric field where it happened to intersect a copper wire. It was the fields themselves that were fundamental, that carried the enormous energy of this force, and he realized the relationship was a beautiful symmetrical dance. A changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. The first is just another way of stating Ørsted's discovery. The second, which Faraday discovered in 1831, is called electromagnetic induction, and it is the very foundation of our technological world. Every power station on Earth, whether it's burning coal or harnessing the power of the atom, uses a source of energy to turn a coil of wire inside a magnetic field. This changing magnetic field creates a changing electric field in the wire, which drives the flow of electrons that we call electricity. This intimate connection is deeper than even Faraday imagined. As Einstein would show in 1905, electricity and magnetism are two sides of the same coin, two facets of a single, unified entity called the electromagnetic force. Just as space and time merge into space-time, so do these two forces. How much electric field and how much magnetic field you perceive depends entirely on your motion relative to their source. But the most remarkable consequence of this dance is the fact that you can comprehend these words at all. In 1863, the Scottish physicist James Clerk Maxwell realized that because a changing electric field creates a magnetic one, which in turn creates an electric one, and so on, you could have a self-perpetuating wave, a ripple that could travel through the electromagnetic field that fills all of space, forever regenerating itself. He calculated the speed of this wave and found it to be the speed of light. Light, he declared, is an electromagnetic wave. Red light is a slowly oscillating wave. Blue light is a rapidly oscillating one. But his equations placed no limits on the frequency of these waves. There could be waves that oscillate far more slowly than red light, and waves that oscillate far more frenetically than blue light. Billions of invisible colors. Radio waves, microwaves, X-rays, gamma rays. This discovery of the electromagnetic spectrum and our ability to harness it created the interconnected world of the 21st century. As Richard Feynman said, from the perspective of 10,000 years from now, the most significant event of the 19th century will be judged to be Maxwell's discovery of the laws of electrodynamics. The killer application for this new power, however, wasn't communication, but the light bulb. It effectively doubled the productivity of humanity by banishing the night. But to power light bulbs in every home, electricity had to be transmitted over long distances, and that was a problem. Thomas Edison championed a system of direct current, where charge flowed in one direction. But the electric field driving the current lost energy over distance, meaning homes far from a power station got dimmer light bulbs. His solution was to build a power station every kilometre or so. It was the Serbian-American genius Nikola Tesla who saw a better way. He realized that if you generate electricity at an extremely high voltage, a very strong electric field, it could lose a lot of energy and still be powerful enough at its destination. The trick was how to step down this high voltage to a safe, usable level for homes. You can't easily do that with direct current, but with alternating current, where the charge is pushed back and forth, you can. By running the current through a coil of wire with many turns, you create a changing magnetic field that induces a current in a nearby second coil with fewer turns. The fewer turns mean a lower voltage. These transformers are the reason electricity can be sent across countries at tens of thousands of volts, and arrive at your home as a safe 240. Tesla's system made the modern world possible. This force, harnessed for technology, is also the central force of nature itself. It's not just the glue that holds atoms together, it's the force that sticks atoms together to form molecules. Chemistry is just the rearrangement of electrons, driven by electrical forces. The very rigidity of your body, the solidity of the ground beneath your feet, is due to the electrical repulsion between the outer electrons of the molecules you're made of. And it goes deeper. Electricity powers life itself. Electrons stripped from the food you eat create electric fields across the walls of your cells, driving the creation of the molecules that power your body. Ultimately, it is a flow of electrons between the neurons in your brain that allows you to process these words, to feel emotion, to lay down memories. We are electrical beings, animated by the same force that lights our cities. We are, in a very real sense, bottled lightning. And this same force, in its manifestation as light, warms our world. But there's a subtlety to how our planet stays habitable. It's not just about the light coming in, it's about the heat that's trying to get out. Molecules in our atmosphere, like carbon dioxide, have this peculiar property. They absorb the heat radiated by the Earth's surface and trap it. They act like a planetary blanket. Without them, particularly water vapor, our world would be a frozen ball of ice, with an average temperature of -18 degrees Celsius. Life as we know it would be impossible. The person who first stumbled upon this was an American scientist named Eunice Foote in 1856. She filled glass tubes with different gases and exposed them to sunlight, discovering that water vapor and carbon dioxide warmed up the most. She speculated that if the amount of these gases in the atmosphere changed, so too would the climate. She was the first person in history to make that connection. A few years later, the Irish physicist John Tyndall independently confirmed her findings but took a crucial step further. He showed that these gases don't absorb the visible light from the sun directly. After all, the atmosphere is transparent. We can perceive the sun and stars through it. Instead, they absorb the invisible infrared radiation, the heat, that is radiated back from the ground after it's been warmed by the sun. As Tyndall wrote, the atmosphere admits the entrance of the solar heat but checks its exit. This is the famous greenhouse effect. Now, a question might occur to you. The most abundant molecules in our air are nitrogen and oxygen, making up 99% of it. Why don't they act as greenhouse gases? The answer is a subtle one to do with molecular structure. Infrared light can only be absorbed if the vibration it causes in a molecule changes the separation between positive and negative charge within that molecule. For the simple symmetrical molecules of nitrogen and oxygen, this doesn't happen. And it's a good thing too. If it did, the Earth would be as hot as an oven. It's astonishing to think that our planet's habitability hinges on the properties of molecules that make up less than 1% of our atmosphere. It was the Swedish chemist Svante Arrhenius who, in 1896, put all the pieces together. He suggested that human activity, specifically the burning of fossil fuels, could release enough carbon dioxide to enhance this natural greenhouse effect and cause what we now call global warming. He was right. Since 1958, we've been measuring carbon dioxide levels directly, and they have risen in lockstep with global temperatures. The evidence is now unequivocal. The Greenland and Antarctic ice sheets are shrinking, glaciers are retreating worldwide, and the Arctic sea ice is in rapid decline. The world's oceans have absorbed much of this excess carbon dioxide, becoming more acidic and putting immense stress on marine life like corals. There is a great irony here, isn't there? The very effect that has kept our planet habitable for over 4 billion years is now, through our actions, threatening the stability of our civilization. There's even a natural regulatory mechanism, a planetary thermostat, that has kept the Earth's temperature stable over geological time. This carbon cycle involves carbon dioxide being pulled from the atmosphere, reacting with rock and water to form carbonates, which are then carried down into the Earth's interior by the slow churn of plate tectonics. This process, however, operates on timescales of millions of years. It's far too slow to cope with the unprecedented rate at which we are pumping carbon dioxide into the atmosphere today. We are overwhelming the planet's natural systems. To understand the stakes, we only have to look at our planetary neighbour, Venus. is almost a twin to Earth in size, and it likely had oceans in its youth. But being closer to the Sun, its oceans evaporated, pumping vast quantities of water vapour, a potent greenhouse gas, into its atmosphere. This triggered a runaway feedback loop. The planet grew hotter, releasing even more trapped gases from its rocks. Until today, it has a crushing atmosphere of almost pure carbon dioxide and a surface hot enough to melt lead. Venus is a stark warning of what can happen when the greenhouse effect goes catastrophically wrong. The existence of this effect also helps solve a long-standing puzzle about our own planet's past, the faint young sun paradox. Our models of stellar evolution tell us that when the Earth was born, the Sun was about 30% fainter than it is today. By rights, the early Earth should have been frozen solid. Yet the geological evidence is clear. There was liquid water on its surface as early as 4.4 billion years ago. The most likely explanation is that the primordial Earth had a much thicker atmosphere, perhaps 70% carbon dioxide from intense volcanic activity, creating a powerful greenhouse effect that compensated for the faint sun. So you see, the story of our world, of its climate and its capacity for life, is deeply entwined with the subtle quantum properties of the molecules that make up its atmosphere. It's a delicate balance, one we are now disrupting at our peril. And the reason our sun is hot, the reason it shines at all, is remarkably simple. It's because it contains an enormous amount of mass. The sheer weight of all that matter crushing down on its core squeezes the material there to an incredible density and heats it to about 15 million degrees. It's the same principle as the air in a bicycle pump getting hot when you compress it. At that temperature, it doesn't matter what the sun is made of. If you gathered a billion tons of baked beans or old television sets and put them in one place, the core would still heat up to 15 million degrees. It's the mass, and only the mass, that dictates the temperature. This simple fact allowed the British astrophysicist Arthur Eddington, back in 1920, to work out the internal structure of the Sun without even knowing what its ultimate power source was. He reasoned that at every point inside the Sun, the inward crush of gravity must be perfectly balanced by the outward push of the hot gas. This allowed him to, in effect, perceive the conditions deep inside a star. But that only explains why the Sun is hot now. It's constantly radiating its heat away into space, so something must be replacing that lost energy. For a long time, this was a profound mystery. If the Sun were a giant lump of coal, it would burn out in a few thousand years. We know the Earth is billions of years old, which means the Sun's power source must be about 1 million times more concentrated than coal. That source, discovered at the dawn of the 20th century, is nuclear energy. The Sun is a gigantic nuclear fusion reactor, powered by gluing together the nuclei of the lightest element, hydrogen, to form the second lightest, helium. The leftover mass from this process is converted into the energy of sunlight, according to Einstein's famous equation, E equals mc squared. The process itself is a multi-step one, and the first step is the real bottleneck. It involves two protons colliding and one of them transforming into a neutron. This transformation can only be accomplished by nature's weak nuclear force, and it's called the weak force for a reason. It's incredibly improbable. A given proton in the Sun's core will, on average, collide with other protons for about 10 billion years before it finally undergoes this fusion reaction. The Sun is about 5 billion years old, so it's roughly halfway through its fuel supply. This incredible inefficiency is actually a blessing. It's what makes the Sun burn so steadily for so long, providing the stable conditions necessary for complex life to evolve on Earth. The weak force, by acting as a cosmic brake on the Sun's furnace, is the reason we are here. For a time, it seemed even this wasn't enough. The temperature at the Sun's core, 15 million degrees, was thought to be 1,000 times too low for protons to overcome their mutual electrical repulsion and get close enough to fuse. The solution came from the strange world of quantum theory. Protons, like all subatomic particles, can behave as waves. This means there's a small but non-zero probability that a proton can simply tunnel through the repulsive energy barrier that separates it from another proton, spontaneously appearing on the other side, close enough for the strong nuclear force to bind them together. It's this quantum tunneling that allows the Sun to shine. and the sun contains its own thermostat. If it generates too much heat, the gas expands and cools, slowing the nuclear reactions down. If it generates too little, it contracts and heats up, speeding them up. It's a beautifully self-regulating system that has provided a stable source of energy for billions of years. But the sun is not just a placid ball of hot gas. It's a seething, dynamic and unpredictable place, and that's because of magnetism. The sun is made of plasma, a gas where electrons are stripped from atoms, meaning it's full of moving electric charges. Moving charges generate magnetic fields, and these fields, in the churning, rotating plasma of the sun, get twisted and tangled up like elastic bands, storing enormous amounts of energy. Where these tangled loops of magnetism break through the surface, we perceive sunspots. When they snap and reconnect, they unleash that stored energy in spectacular solar flares, hurling plasma at 1,000,000 degrees for tens of thousands of kilometers into space. There's even 1,000,000-mile-an-hour solar wind blowing constantly from the sun, carrying its magnetic field out past all the planets. We live inside the sun's extended atmosphere. Understanding this space weather is not just an academic exercise. Our technological civilization is critically dependent on it. Occasionally, the sun unleashes a coronal mass ejection, a vast blob of plasma and magnetic field, a Mount Everest of matter hurled into space at hundreds of times the speed of a passenger jet. In 1859, one such event, the Carrington event, struck the Earth. It caused telegraph systems to burst into flames and auroras so bright you could read a newspaper by them at midnight in the Caribbean. In 1859, the world wasn't so dependent on technology. Today, a similar event could cripple our power grids, destroy our satellite networks, and send our interconnected world back to a pre-electrical age. The very star that gives us life could, in a cosmic blink, take away the foundations of our civilization. This flow of energy from the sun, outwards into the cold of space, is an example of a universal principle so fundamental, so profound, that it governs everything from a star to a crumbling castle, to the unfolding of life itself. It dictates the direction of time. It's called the second law of thermodynamics, and it explains why things fall apart, why eggs break and don't unbreak, why people grow old and not young. You might think this is just common sense, but to a physicist it was a deep mystery for a very long time. The fundamental laws of physics, like gravity or electromagnetism, are time-symmetric. They work just as well forwards as they do backwards. A video of a planet orbiting a star played in reverse looks perfectly plausible. But a video of a shattered vase reassembling itself from its pieces is utterly impossible. So why the difference? What is it that imposes this one-way direction, this arrow on time? The answer is breathtakingly simple, and it comes down to probability. Think about that broken vase. It could have shattered into one large piece and 10 small ones, or 2 big pieces and 5 small ones, or 100 tiny fragments. There are a vast, almost infinite number of ways for a vase to be broken. Now think of an intact vase. There is only one way for it to be intact. If all these states, intact or broken in some way, are equally likely, then it is overwhelmingly, fantastically more probable that the vase will be in one of its countless broken states than in its single intact one. That's it. That's the second law. Things move from order to disorder because there are just so many more ways to be disordered. Physicists have a technical term for this disorder: entropy. The second law states simply that in a closed system, entropy never decreases. It always increases. It's a law of such supreme importance that the physicist Arthur Eddington once said that if your theory is found to be against the second law of thermodynamics, there is nothing for it but to collapse in deepest humiliation. But this raises a question, doesn't it? If the universe is constantly moving towards a state of greater disorder, how do you explain the existence of order? How do you explain a tree, a city, a human being? How do you explain life, which seems to be the very antithesis of this slide into chaos? Life creates and maintains incredible structures of order. It seems to defy the second law. The answer is that life doesn't break the law, it exploits a loophole. The second law only says that the total entropy of a closed system must increase. It doesn't forbid the creation of pockets of order. as long as that order is paid for by creating an even greater amount of disorder somewhere else. Life, in short, exports disorder to the universe. Think of the Earth. It receives high-quality, high-energy photons from the sun. Life harnesses this energy to build complex ordered structures: plants, animals, us. In the process, that energy is degraded, and the Earth radiates it back into space as low-quality, low-energy infrared photons. For every one high-quality photon we receive, we radiate about 20 low-quality ones back out. The total energy is balanced, but the total disorder, the entropy of the universe, has increased. We are islands of order in a cosmic ocean of increasing chaos, and we are powered by the temperature difference between the hot sun and the cold of deep space. Ultimately, this process has a final destination. One day, all the stars will have burned out, all their energy will have radiated away into the void. The universe will reach a state of maximum entropy, where the temperature is the same everywhere. With no temperature differences, no work can be done. All activity will cease. This state of ultimate cosmic ennui is known as the heat death of the universe. The world will end not with a bang, but a whimper. But why is the universe getting more disordered today? The only possible answer is that it was more ordered in the past. This implies that the universe began in a very special, highly ordered, low-entropy state at the Big Bang. And that is a deep puzzle that we still don't have an answer for. So, the next time your coffee cools on the table, or you reflect on the passage of time, remember that the reason for this everyday experience is rooted in the most profound fact about our cosmos, that it began in a Big Bang. The crumbling of a castle is connected to the expansion of the universe. Can there be a more striking connection between the intimate and the cosmic? The very rock of that castle, the ground on which it was built, is itself part of a story of constant change, a story of a planet that is anything but solid and static. The surface of our Earth isn't a single solid shell. It's fractured into a mosaic of massive plates, like a crazy paving, all jostling and grinding against each other. This idea, plate tectonics, was once considered heresy, but it explains almost everything we perceive about the geology of our world. The first person to have an inkling of this was a German climatologist named Alfred Wegener in 1912. He noticed, as others had before him, the uncanny jigsaw puzzle fit of the coastlines of South America and Africa. But Wegener went further. He saw that the rock types and the fossils found on both continents matched up perfectly. He proposed that they were once joined and had since drifted apart. His theory of continental drift was dismissed as lunacy. How could entire continents plough through the solid seabed? Wegener had no mechanism, and he died long before he was vindicated. The proof came from the depths of the oceans. In the 1960s, detailed surveys of the Atlantic seabed revealed a vast underwater mountain range running down its centre, the Mid-Atlantic Ridge. And when geologists measured the magnetism of the rocks on the seafloor, they found a stunning pattern: symmetrical stripes of rock with alternating magnetic polarity fanned out from either side of the ridge. We now know that the Earth's magnetic field periodically flips. As new molten rock erupts at the ridge and solidifies, it locks in the direction of the magnetic field at that time. The stripes were a magnetic tape recording of the Earth's history, and they showed that the youngest rock was at the ridge itself, with progressively older rock further away. The conclusion was inescapable. The Mid-Atlantic Ridge was a giant factory, constantly creating new crust and pushing the continents apart. South America and Africa didn't have to plough through the seabed. The seabed itself was forming between them, pushing them apart like two objects on an expanding conveyor belt. But if new crust is constantly being created, it must be destroyed somewhere else. Our planet isn't getting any bigger. The Earth's plates float on the hot, viscous mantle beneath, and there are two types of crust: lighter continental crust, made of granite, and denser oceanic crust, made of volcanic basalt. This difference in density is why the continents are high and dry, while the ocean floors are low and wet. When two plates collide, one of three things can happen. If two continents collide, the light crust has nowhere to go but up, buckling and folding to create great mountain ranges like the Himalayas. If two plates slide past each other, like at the San Andreas Fault in California, they build up immense tension that is released in earthquakes. And if a dense oceanic plate collides with a lighter continental plate, the oceanic plate dives down beneath it, into the mantle, in a process called subduction. As this slab of crust descends, it melts, creating the magma that feeds the volcanoes that line so many continental edges like the Andes. The constant snagging and juddering of this descending plate is what generates the most powerful earthquakes on the planet. The whole system is driven by the Earth's internal heat, the remnant heat from its formation, and the heat from radioactive decay in its core, which sets up slow, churning convection currents in the mantle that drag the plates along. This restless geology does more than just reshape the surface. It's crucial for keeping our planet habitable. The plate tectonic conveyor belt plays a key role in the carbon cycle, dragging carbon-rich sediments down into the mantle and preventing a runaway greenhouse effect like the one on Venus. Plate tectonics might be a fundamental requirement for a world to sustain a rich diversity of life over geological timescales. It is the engine that drives the planetary life support system. It is the reason our world is not a dead static rock, but a dynamic living planet. And yet, for all the grandeur of this planetary motion, for all the power of these continent-sized plates, the world they create is built from something unimaginably small. It's built from atoms. But what happens when we probe the world of the atom itself? What laws govern that realm? We find a world that defies all our everyday intuition, a world of shimmering probabilities and ghostly connections. We find the world of quantum theory, and the central, baffling truth of this world is that its ultimate constituents, electrons, photons, the very building blocks of reality, can behave both as localized particles like tiny billiard balls and as spread out waves like ripples on a pond. Now don't even try to form a mental picture of how a single thing can be both a tiny point and a diffuse wave at the same time. You can't. The entities of the quantum world are neither particles nor waves. They are something else entirely, something for which we have no word and no everyday analogy. And perhaps that shouldn't surprise us. An atom is so small that 10 million of them could fit side by side across the full stop at the end of this sentence. Why should the rules that govern such a minuscule realm bear any resemblance to our own coarse macroscopic world? This theory, as strange as it is spectacularly successful. It has given us lasers, computers, and nuclear power. It explains why the ground is solid and why the sun shines. But more than that, it gives us a glimpse into a bizarre Alice in Wonderland reality that lies just beneath the surface of everything we perceive. It's a world where a single atom can be in two places at once, a world where events can happen for no reason at all, and a world where two particles can be linked in such a way that measuring one instantaneously affects the other, even if they are on opposite sides of the universe. All this weirdness flows from that central fact of wave-particle duality. Let's start with light. We know from Thomas Young's famous double-slit experiment in 1801 that light can behave as a wave, but it can also behave as a stream of particles which we call photons. Now consider something utterly mundane, a pane of glass. When you peer through a window, most of the light passes through, but you also perceive a faint reflection of yourself. If light is a wave, this is easy to understand. Part of the wave is transmitted, part is reflected. But if light is a stream of identical photons, what does this mean? Why are some transmitted and some reflected? They are all identical, so they should all do the same thing. The only possible conclusion is that for any individual photon, its behavior is fundamentally unpredictable. There is a certain probability that it will pass through, and a certain probability that it will be reflected. We can never know what a single photon will do. At its most fundamental level, the universe is governed by random chance. This deeply unsettled Einstein, who famously declared that God does not play dice, but all the evidence suggests that he does. Now, let's consider the other side of the coin. Particles behaving as waves. This means they can do things that only waves can do. One of those things is superposition. If a wave can be in state A, and it can be in state B, it can also be in a combination, or superposition, of A and B at the same time. For the quantum wave of a particle, which describes the probability of finding it somewhere, this has a staggering implication. A quantum wave that describes an electron being on the left side of a room and another that describes it on the right can be combined. The result is a wave that describes the electron being on both the left and the right side of the room simultaneously, in two places at once. This is the basis of quantum computing, which seeks to harness this ability to perform many calculations simultaneously. This quantum weirdness is fragile. Any interaction with the outside world, bouncing a photon off it to observe it, for instance, forces the particle to choose a single state. The superposition collapses. But before that collapse, the different possibilities, the different coexisting waves, can interfere with each other. A wave representing one possible outcome can cancel out or reinforce a wave representing another. And this interference is what makes the quantum world so radically different from our own. It's why atoms are stable. In a classical pre-quantum picture, an orbiting electron should radiate away its energy and spiral into the nucleus in a fraction of a second. The world as we know it shouldn't exist. The reason it does is that when you combine all the infinite possible paths an electron could take, all the different quantum waves, they destructively interfere and cancel each other out close to the nucleus. The probability of the electron spiraling in is zero. The solidity of the world is a consequence of this ghostly quantum interference. There's another consequence of this wave-like nature, known as the Heisenberg uncertainty principle. You cannot simultaneously know certain pairs of properties of a particle, like its precise position and its precise momentum, with perfect accuracy. The more you pin down one, the fuzzier the other becomes. It's a fundamental trade-off built into the fabric of reality. This principle has a mind-bending implication for empty space. If you try to pin down a location in the vacuum, you become hugely uncertain about the energy contained there. This means the vacuum is not empty. It seethes with a constant fizz of virtual particles popping into and out of existence for fleeting moments. This isn't just a theorist's fantasy. This vacuum energy has real, measurable effects on the atoms around us. The void is not a void. It is a turbulent sea of quantum potential. This quantum world, strange as it is, provides the alphabet of nature, the fundamental components from which everything is built. The idea that the world is made of fundamental, uncuttable building blocks is an ancient one. Around 440 BC, the Greek philosopher Democritus wondered what would happen if you kept cutting a piece of matter in half. He concluded that you couldn't do it forever. Eventually, you would reach an indivisible grain, which he called an atom. For over 2 millennia, this was just a philosophical idea, but gradually evidence mounted. The behavior of gases, the jiggling of pollen grains in water known as Brownian motion, all could be explained if matter was made of countless tiny frenetic particles. Finally, in 1981, with the invention of the scanning tunneling microscope, we could for the first time directly perceive these atoms, arrayed like tiny footballs on a surface. Democritus was right, but he also guessed that these atoms came in a limited number of types, and that the bewildering complexity of the world was just an illusion, a reflection of the endless ways you could combine these few basic building blocks. By arranging them in different ways, you could make a rose, or a galaxy, or a newborn baby. In the 18th century, Antoine Lavoisier listed 23 of these elemental substances. Today, we know of 92 that occur naturally, but even 92 seemed like a lot. A hint that atoms themselves might be made of smaller things came from the periodic table, devised by Dmitri Mendeleev in 1869. He arranged the known elements in order of increasing weight and noticed that their properties repeated in a regular periodic pattern. Such a pattern in nature almost always signals a simpler underlying structure. Atoms, it seemed, were not the final indivisible layer of reality, and so it proved. We discovered the electron, and then the atomic nucleus, a tiny, dense core containing almost all the atom's mass, with the electrons orbiting it like distant planets. This nucleus is made of protons and neutrons. It is the number of protons in the nucleus that defines an element. Hydrogen has 1, carbon has 6, uranium has 92. But why don't all the electrons in an atom just pile into the lowest energy orbit around the nucleus? If they did, all atoms would have the same outer shell of electrons, and so they would all behave chemically in the same way. The rich variety of the world would be gone. The reason they don't is another strange quantum rule, the Pauli exclusion principle. It dictates that no two identical electrons can occupy the same quantum state. They are forced to arrange themselves in shells at successively greater distances from the nucleus. This is what gives each element its unique chemical personality. It's the reason we have chemistry at all. But even these particles, protons and neutrons, are not fundamental. They are made of even smaller things called quarks. And here, we reach what we currently believe is the bottom rung of nature's ladder. All the stable matter in the universe, everything you've ever touched or experienced, is made from the endless permutations of just three fundamental particles: the up quark, the down quark, and the electron. Democritus, 2.5 millennia ago, was, in his essence, completely correct. The staggering complexity and beauty of the world emerge from the combinatorial possibilities of an astonishingly simple alphabet. And perhaps the most complex and beautiful structure ever to arise from this simple alphabet is life itself. And the mechanism that has sculpted life, that has driven it from a single ancestral cell to the bewildering diversity we perceive today, is another idea of breathtaking simplicity: evolution by natural selection. Why are living things so perfectly suited to their environment? For the same reason that a racehorse is suited to running fast. Over generations, breeders select the fastest horses and breed them together. Charles Darwin's genius was to realize that nature does the same thing. But instead of a breeder, the selector is the environment itself. The logic is inescapable. Organisms produce far more offspring than can possibly survive on the available resources. There is a constant struggle for existence. Within any population, there is natural variation. Individuals are not identical. Some of those variations will, by pure chance, make an individual slightly better at competing for those scarce resources, better at finding food, better at avoiding predators, better at attracting a mate. Those individuals will be more likely to survive and reproduce, and crucially, they will pass those advantageous traits on to their offspring. Over successive generations, these successful traits become more common in the population. That's it. That's natural selection. It is a simple, blind, algorithmic process that, given enough time, can generate creatures of stupendous complexity and with the powerful illusion of design. It is, as Richard Dawkins calls it, the greatest idea in the history of science. Darwin came to this idea after his voyage on HMS Beagle, particularly his observations of the finches on the Galapagos Islands. He saw that on each island, the finches had beaks that were perfectly adapted to the local food source. He realized they must have all descended from a common ancestor from the mainland and had diversified to fill the available ecological niches. The idea was so revolutionary, so at odds with the religious doctrine of his time, that he sat on it for 2 decades. It was only when he learned that another naturalist, Alfred Russel Wallace, had independently arrived at the same idea that Darwin was spurred to publish his masterwork on the origin of species in 1859. His theory stated that all life on Earth is related, descended from a common ancestor over vast spans of time. Humans were not a special creation, made in God's image, but just another branch on the great tree of life, another animal. But Darwin's theory, for all its power, had 2 missing pieces. He didn't know the source of the variation on which selection could act, and he didn't know the mechanism of inheritance. The answers to both came from the work of an Augustinian friar, Gregor Mendel, who, unknown to Darwin, was meticulously crossbreeding pea plants in his monastery garden. He discovered that traits are not blended but are passed down in discrete packets, which we now call genes. And the mechanism for variation lies in the copying of these genes. The instruction manual for life is written in a molecule called DNA, a 4-letter code 3 billion letters long in humans. When this code is copied from parent to offspring, small, random errors, mutations, inevitably occur. Most of these mutations are neutral or harmful, but very occasionally one will provide a small advantage. And it is this constant supply of random mutation that provides the raw material for natural selection to work on. The fusion of Darwin's idea with the science of genetics in the 20th century created the modern synthesis of evolutionary biology, one of the most robust and well-supported theories in all of science. It tells us that every cell in your body is a direct descendant of the first life that emerged on this planet some 4 billion years ago. This brings us to one of the most consequential ideas in all of science, an idea that forced us to completely rethink our understanding of space, time, and reality itself. And it all stems from a simple, unshakable fact. Light is uncatchable. Albert Einstein, as a teenager, wondered what you would perceive if you could ride alongside a beam of light. According to Maxwell's theory, light is a self-propagating electromagnetic wave. If you could catch up to it, you would perceive a stationary frozen wave, but Maxwell's equations do not allow for such a thing. A light wave that isn't moving isn't a light wave. From this paradox, Einstein concluded that it must be impossible to catch up to light. Its speed in a vacuum must be absolute. It must be the same for all observers, no matter how fast they are moving. This simple postulate has earth-shattering consequences. Speed is distance divided by time. If everyone, regardless of their own motion, measures the exact same speed for light, then their measurements of distance and time must be changing to compensate. Imagine a clock on a very fast-moving train, a clock made of a pulse of light bouncing between two mirrors. For a passenger on the train, the light travels a simple up and down path. But for someone standing by the track, perceiving the train rush past, the light pulse has to travel a longer diagonal path to catch up with the moving mirrors. Since the speed of light is constant for both observers, the only way this can be true is if time itself is running slower for the passenger on the train from the perspective of the person on the platform. Time is not absolute. Your clock ticks at a different rate to mine depending on our relative motion. This is time dilation. Correspondingly, space contracts in the direction of motion. This is Lorentz contraction. Space and time are not a fixed universal backdrop to events. They are mutable, dynamic, and relative to the observer. They are different threads of a single, unified fabric, space-time. This isn't just a theoretical curiosity, it's a measured fact of our universe. Atomic clocks on aeroplanes run slightly slower than those on the ground. Unstable subatomic particles called muons, created at the top of our atmosphere and travelling at near-light speed, should decay long before they reach the ground. But from our perspective, their internal clocks are running so slowly that they survive the journey. From the muon's perspective, its clock is normal, but the atmosphere is rushing towards it, and the distance to the ground is contracted, allowing it to reach the surface in its short lifespan. Both perspectives give the right answer. That's the magic of relativity. And there's one more consequence, perhaps the most famous of all. What is it that stops you from accelerating a massive object all the way up to the speed of light? As you push it faster and faster, it must resist that acceleration more and more. Its inertia, its mass, must increase. The energy of motion you're putting into it is manifesting as additional mass. Energy has mass, and by the same token, mass has energy. An incredible amount of it, locked away, as expressed in the most famous equation in physics, E equals mc squared. This is the secret of the stars. It's the power of the atom. It's a direct consequence of the simple fact that you can't catch a beam of light. And this incredible universe, governed by these strange and wonderful laws, has produced perhaps its most complex and mysterious object, the human brain. It's made of about 100 billion neurons, but it's not the number that matters, it's the connections. Each neuron can be connected to 10,000 others, creating a network of some 1,000 trillion connections. It is in the strengths of these connections that all our knowledge, our memories, our very selves are encoded. And the most remarkable thing about the brain is that its principal activity is making changes in itself. Every experience you have, reading these words, having a conversation, listening to a piece of music, physically alters your brain. It strengthens some connections and weakens others. This ability to constantly rewire itself is known as neuroplasticity. When you learn something new, you are forging and reinforcing pathways in this vast neural network. Repetition strengthens these pathways, which is why practice is so essential for learning a skill. The skill becomes hardwired, automatic, encoded in the physical structure of your brain. A memory is not a thing stored in a specific location. It is a pattern of connections distributed across billions of neurons. And just as connections are strengthened to form memories, they can be pruned back when they are no longer useful. That is the process of forgetting. Our brain is a self-programming computer. A baby is born with a vast potential for connection, a blank slate. Its experiences of the world, the sights, the sounds, the touches, are what write the program, shaping the neural architecture that will become its unique mind. This plasticity continues throughout our lives. It's how stroke victims can sometimes recover lost functions, as healthy areas of the brain take over the tasks of damaged regions. The brain is the ultimate lump of programmable matter, and it performs this incredible feat of computation using only about 20 watts of power, the equivalent of a dim light bulb. It is 10,000 times more energy efficient than a supercomputer of comparable power. This incredible efficiency comes at a cost, however. The brain is an energy hog. Though it's only about 2% of our body weight, it consumes 20% of our oxygen. This is why most organisms don't have brains. They are an expensive luxury, only necessary for creatures that move actively and need to predict and navigate a complex environment. It's a sobering thought that the very organ that allows us to contemplate the universe is a product of the brutal evolutionary imperative to find the next meal and avoid becoming one. But can this organ, this product of evolution, ever truly understand itself? Is it possible for a system to create a complete model of its own workings? Or are we, as some have suggested, like a person trying to lift themselves into the air by pulling on their own shoelaces? That remains one of the great unanswered questions. But our understanding of gravity, the force that shapes the cosmos, was not yet complete with Einstein's special relativity. His theory of 1905 dealt with constant motion. But what about acceleration? What about gravity? It took him another 10 years of intense struggle to arrive at his general theory of relativity, and the key insight, what he called the happiest thought of his life, came from a simple realization. A person in freefall feels no gravity. They are weightless. Imagine an astronaut in a windowless spaceship far from any planet. If the spaceship is accelerating upwards, the astronaut will feel pressed to the floor exactly as if they were standing on Earth. They cannot tell the difference. If they drop a hammer and a feather, they will appear to fall and hit the floor at the same time, not because a force is pulling them down, but because the floor is accelerating up to meet them. Einstein realized that these two situations, being in a gravitational field and being in an accelerated frame of reference, are not just indistinguishable, they are equivalent, they are the same thing. Gravity, he concluded, is not a force in the traditional sense, it is the manifestation of acceleration. But how can we be accelerating while standing still on the surface of the Earth? The answer is that we are moving through a curved space-time. The mass of the Earth doesn't create a force that reaches out and pulls you down. It creates a valley, a warp, in the four-dimensional fabric of space-time around it. And your natural path through this curved space-time is downwards, towards the center of the Earth. The only thing stopping you is the ground beneath your feet, which is constantly pushing up on you, constantly accelerating you. That feeling of weight is the feeling of the Earth's surface preventing you from following your natural path through curved space-time. The Earth itself isn't pulled by the Sun, it's following the straightest possible path, a geodesic, through the space-time curved by the Sun's mass, like a ball rolling around the inside of a roulette wheel. Matter tells space-time how to curve, and curved space-time tells matter how to move. One of the most profound consequences of this is that gravity affects time itself. A clock closer to a massive object, where space-time is more curved, will tick more slowly than a clock further away. You age ever so slightly slower on the ground floor of a building than you do on the top floor. The effect is minuscule, but it has been measured with hyper-accurate atomic clocks. And this principle is essential for technologies we use every day. The GPS satellites that guide our cars and planes are in a weaker gravitational field and are moving at high speed. both special and general relativity must be taken into account to correct their clocks. Without Einstein's understanding of gravity as curved space-time, your GPS would be inaccurate by several kilometers every day. And this story of our origins, this cosmic and biological lineage, brings us to the story of ourselves, the species Homo sapiens. It's a story characterized by 3 words: migration, migration, migration. About 7 million years ago in Africa, our evolutionary line split from that of the chimpanzees. Over the subsequent millions of years, a succession of our hominin ancestors spread out from that African cradle in multiple waves. For most of our history, we have shared the planet with several other human species. Today, we are the last one standing. The first great innovation was walking on 2 legs, freeing our hands to make tools and carry food. The next was the taming of fire and the invention of cooking, which provided more energy from our food. This extra energy fueled the dramatic expansion of our brains. With bigger brains came more complex social structures, cooperation, and eventually, language. Our own species, Homo sapiens, arose in Africa about 300,000 years ago. When we left the continent some 60,000 years ago, we were not alone. We encountered and interbred with other humans, like the Neanderthals in Europe and the Denisovans in Asia. About 2% of the DNA of modern non-Africans is Neanderthal. In a real sense, they did not die out completely. A part of them lives on in us. Why did we survive while all the others vanished? We don't know for sure. But one intriguing possibility is our extended childhood. We are born earlier in our development than other hominins were, with brains that are still highly plastic. This long period of learning and adaptation may have given us a crucial edge in a rapidly changing world. It's a fascinating thought that the key to our species' dominance might be our prolonged period of youthful vulnerability and dependence. And today, we are the sole inheritors of a planet, a single, globally interconnected species with the capacity to understand our own origins, to comprehend the laws that govern the cosmos and to shape our own future. And as we look to that future, our deepening understanding of the quantum world is opening the door to a new kind of technology, one that could be as revolutionary as the discovery of electricity, the quantum computer. A conventional computer works with bits, which can be either a 0 or a 1. A quantum computer works with qubits, which, thanks to the principle of superposition, can be a 0 and a 1 at the same time. This means a single qubit can be involved in 2 calculations at once. 2 qubits can do 4 calculations, 3 can do 8. With each additional qubit, the computer's power doubles. This exponential growth is what gives quantum computers their almost unimaginable potential. A machine with only a few hundred stable qubits could perform more simultaneous calculations than there are atoms in the known universe. The Oxford physicist David Deutsch argues that this forces us to confront a startling possibility. Where is the computer performing these calculations? The universe itself doesn't contain enough resources. His answer is that the quantum computer is harnessing the resources of parallel universes, tapping into the computational power of trillions of other realities that have split off from our own. Whether you accept this many worlds interpretation or not, the power is real. The challenges in building such a machine are immense. Qubits are incredibly fragile and lose their quantum properties at the slightest disturbance from their environment. But the progress is relentless. And even if a general-purpose quantum computer remains a distant dream, a more limited version could still change the world. There is one thing a quantum computer will be brilliant at: simulating other quantum systems. We could design new medicines, create new materials with incredible properties, and develop super-efficient catalysts to solve our energy and climate problems, all by accurately modelling the behaviour of molecules at the quantum level. It's a technology that is still in its infancy, but it promises to give us an unprecedented mastery over the material world. Our mastery of the physical world is built on understanding the forces that govern it. We've spoken of gravity and electromagnetism, but there are 2 others that operate only within the confines of the atomic nucleus. These, along with the particles they act upon, are described by what is, despite its humble name, the most successful scientific theory ever devised: the Standard Model of Particle Physics. It tells us that everything is made from a small number of fundamental particles, divided into 2 families: fermions, which are the particles of matter like electrons and quarks, and bosons, which are the particles that carry the forces between them. All the stable matter in the universe is made of just 3 fermions: the up quark, the down quark, and the electron. Protons and neutrons are made of quarks held together by the strong nuclear force, carried by a boson called the gluon. This force is so strong that it's impossible to pull a quark out of a proton. They are permanently confined. The other nuclear force is the weak force. It doesn't bind things together, but it allows particles to change their identity. It's the weak force that allows a neutron to turn into a proton, a process that is crucial for the nuclear reactions that power the sun. The weak force is carried by 3 heavy bosons, and then there is the most famous boson of all, the Higgs boson. The Standard Model, in its purest form, requires all these fundamental particles to be massless. This is clearly not true. The Higgs boson is the particle associated with a field that pervades all of space, the Higgs field. It is by interacting with this field that fundamental particles acquire their mass. You can think of it as a kind of cosmic treacle. Some particles move through it easily and have little mass, while others struggle and have a lot of mass. The discovery of the Higgs boson at CERN in 2012 was the final triumphant confirmation of the Standard Model. It's a theory that describes the world we perceive with stunning accuracy, but we know it's incomplete. It doesn't include gravity. It doesn't explain why the particles have the masses they do. And most profoundly, it only describes about 5% of the universe. The rest is made of mysterious dark matter and dark energy, substances whose existence we can infer from their gravitational effects, but whose nature remains a complete mystery. The Standard Model is a magnificent achievement, but it's also a lighthouse illuminating a vast ocean of our ignorance. And just as Einstein's theory of gravity as curved space-time predicted a new kind of radiation, ripples in space-time itself, our universe has now spoken to us in a new language. These are gravitational waves. Imagine space-time as the skin of a drum. Any accelerating mass will cause that drum skin to vibrate, sending out ripples at the speed of light. The problem is that space-time is incredibly stiff, a billion times stiffer than steel. So you need truly cataclysmic events to generate waves that are strong enough for us to detect. You need the collision and merger of black holes. On the 14th of September, 2015, for the first time, we detected such an event. 2 detectors in the United States, each a giant L-shaped instrument with 4-kilometer-long arms, registered a tiny shudder, a stretching and squeezing of space by less than 100 millionth of the diameter of an atom. The signal was the unmistakable death spiral of 2 black holes, each about 30 times the mass of the Sun, merging into one in a distant galaxy over 1 billion years ago. In that final fraction of a second, an amount of energy equivalent to 3 times the mass of our Sun was converted purely into gravitational waves, briefly outshining all the stars in the observable universe combined. Since then, we have detected dozens more of these events, including the collision of neutron stars, which we now know are the cosmic forges that create most of the heavy elements in the universe, like gold and platinum. The gold in a wedding ring was likely created in the violent merger of 2 dead stars. We have opened a new window on the cosmos. For all of human history, we have been looking at the universe. Now, for the first time, we can listen to it. This cosmic symphony is played by an orchestra of fundamental particles, and for every particle of matter, there exists a curious mirror image, an antiparticle. This is the world of antimatter. The existence of this shadow world was first predicted by the British physicist Paul Dirac in 1928. He was trying to write down an equation that described the electron in a way that was consistent with both quantum mechanics and special relativity. The equation he derived was beautiful, but it had a strange quirk. It had 2 solutions. One described the familiar negatively charged electron. The other seemed to describe an electron with positive charge. At first, no one knew what to make of it. Then, in 1932, the American physicist Carl Anderson, while studying cosmic rays, discovered a particle with the same mass as an electron, but with a positive charge. He had found Dirac's antiparticle, the positron. We now know that every particle has an antiparticle. There are antiprotons, antineutrons, antiquarks. When a particle meets its antiparticle, they annihilate each other in a flash of pure energy. This is the most efficient energy release possible, converting 100% of their mass into energy. Conversely, energy can be converted into matter, but only if you create a particle and an antiparticle in a pair, so that properties like electric charge are conserved. This raises one of the biggest mysteries in all of cosmology. The laws of physics as we know them seem to produce matter and antimatter in equal amounts, so in the Big Bang, equal amounts should have been created. But if that had happened, they would all have annihilated, leaving a universe filled with nothing but light. Yet, here we are. We live in a universe made almost exclusively of matter. For some reason, in the very early universe, there must have been a slight asymmetry, a tiny preference for matter over antimatter. For every 10 billion antiparticles, 10 billion and 1 particles of matter were created. After the Great Annihilation, that 1 in 10 billion surplus was left over to form all the galaxies, stars and planets we perceive today. We are the leftover crumbs from a cosmic feast. We still don't know what caused this crucial imbalance. It's a mystery that points to new physics, beyond what we currently understand. And there is one particle that is perhaps the most mysterious and elusive of them all, a true ghost in the cosmic machine, the neutrino. Every second, 100 billion of them are streaming through your thumbnail, having travelled from the heart of the sun in just over 8 minutes. They interact so weakly with other matter that the vast majority pass straight through the entire Earth without noticing it is there. Their existence was first proposed by Wolfgang Pauli in 1930 as a desperate remedy to solve a puzzle in radioactive decay. He was so unsure of his idea that he bet a case of champagne that no one would ever detect one. It took 26 years, but they were detected, flowing in vast numbers from a nuclear reactor. We now know that neutrinos come in 3 types, or flavors, and that they can spontaneously change from one flavor to another as they travel. This ability to change implies that they must have mass, albeit an incredibly tiny amount, about 1,000,000 times less than an electron. This is another deep puzzle, because the Standard Model predicts they should be massless. Neutrinos may be a portal to understanding physics beyond the Standard Model. They're also cosmic messengers of incredible power. Because they travel in straight lines from their source, unaffected by intervening matter or magnetic fields, they allow us to peer into the most violent and energetic processes in the universe, into the fiery core of our own sun, and out to exploding stars and the hearts of active galaxies. They're giving us a new way to perceive the universe, a neutrino-eyed view. They are the shyest of particles, but they may hold the answers to some of the deepest questions we can ask. And all these stories, of forces and particles, of life and planets, of space and time, all converge on a single astonishing point of origin. The greatest discovery of science is that our universe had a beginning. There was a day without a yesterday. About 13.82 billion years ago, everything we can perceive, all matter, all energy, space and time itself, erupted into existence from an unimaginably hot, dense state. This was the Big Bang. This wasn't an explosion in space. It was the explosion of space. It happened everywhere at once. The evidence for this is overwhelming. In 1929, Edwin Hubble discovered that distant galaxies are all rushing away from us. The universe is expanding. If you run the movie backwards, everything must have been closer together in the past. And in 1965, 2 radio astronomers accidentally discovered the faint afterglow of that initial fireball, a whisper of microwaves coming from all directions in the sky. It is the oldest light in the universe, the cosmic microwave background radiation. Our universe was forged in that primeval fire. In the first few minutes, it was hot enough for nuclear fusion to occur, creating all the hydrogen and helium that make up the vast majority of the atomic matter in the cosmos today. All the heavier elements, the carbon in your body, the oxygen you breathe, the iron in your blood, were cooked up later in the hearts of stars and scattered across space when those stars exploded. As the astronomer Carl Sagan famously said, "We are made of star stuff." The basic Big Bang picture is now beyond dispute, but our modern understanding includes some crucial additions. We've learned that the expansion is not slowing down, as you might expect due to gravity's pull. It's accelerating, driven by a mysterious dark energy that seems to be a property of space itself. And we've learned that galaxies couldn't have formed as quickly as they did without the gravitational scaffolding of an invisible dark matter. And we believe that in the very first fraction of a second, the universe underwent a period of hyper-fast expansion called inflation, which stretched it from a subatomic size to something vast in an instant. This inflationary theory suggests that our Big Bang may not have been a one-off event, but that our universe is just one bubble in an eternally inflating multiverse of countless other universes. So, here we are, inhabitants of a small planet orbiting an ordinary star in an unremarkable galaxy, one of trillions in an expanding universe that began 13.82 billion years ago. We are the products of an unbroken chain of cosmic and biological evolution. We are collections of atoms forged in the hearts of long-dead stars, animated by the laws of physics. And we have, through the power of reason and curiosity, managed to piece together this incredible story, this grand narrative of our origins. It is a story filled with mystery and wonder, and it is the greatest story ever told. And the most remarkable thing of all is that we are a part of it.